All right, so today is topic 31. Remember that we did topic 32 a couple of weeks back. So actually the same code is in here. I just moved it from this notebook to another notebook. So if you're curious why that's there, that's why. But today we're talking about our last classification algorithm, which is support vector machines. And part of that, we're going to talk about how the algorithm works and some common use cases of SVMs as well. So there are a couple layers to SVM. So first we're going to talk about the most basic SVM, which is a maximal margin classifier or a support vector classifier. We'll talk about soft margins, the kernel trick, which is something that's really interesting. The kernel trick, we won't get into the math of it, but we'll think conceptually how that might help a classifier. And then we'll just work through some really quick implementation. At this stage, we all know how to implement these circular models. So we'll just do a really quick example. All right, so SVMs, basically, SVMs is actually an entire group of models. Anything that has the idea of trying to separate your data with a plane, that is under the umbrella of an SVM. So over here, you can see that SVMs approaches classification in a very, very direct way. Basically, we're trying to find a plane that separates the classes in the feature space, which to us, we can only really see up to 3D. But imagine if you have like a bunch of points floating around in air, you're just trying to build one, we're just trying to take like a piece of paper and like divide all your points up. And this paper can be like bent at different angles or different angles in 3D space, basically. So that's the whole idea and concept of all support vector machines. So if we can't directly divide our data into two with a flat plane, of course, we can do one of two things because data is never perfectly separable, as we know. We can do one of two things. One, we're going to soften what it means by separates, and we'll talk about that later. And then we'll also talk about enlarging the feature space, which is a very, very abstract concept, but we'll get to it in the middle end of this notebook. All right, so for some terminology, let me zoom in for this. Support vector machines are sometimes used as a general method that incorporates the maximal margin classifier, support classifiers, etc. However, strictly by definition, support vector machine is a support vector classifier with a non-linear kernel. So what these kernels are, we'll talk about later, but the most basic form of an SVM, a support vector machine, is a support vector classifier. Now, this kernel thing that we're going to talk about later is anything that deals with higher dimensions. So whenever, we'll come back to this definition in a little bit. So as long as a support vector classifier is combined with a nonlinear kernel, we'll talk about nonlinear kernels later, the resulting classifier then is known as support vector machine. So you'll see that the term SVM gets thrown around a good bit for any of these sorts of models, but technically it does highly depend on what your exact kernel is, and what kernel is we'll talk about again. All right, so the idea of all SVMs is we're trying to take a plane, flat piece of surface, and divide our data perfectly. So in a p-dimensional space, so p dimensions, number of features that you have, the hyperplane is a subspace defined as p-1. Mathematically, you can actually define a plane with this equation. As you can see, this equation is a linear equation, right? You have your betas, and very similar to what we did with linear regression, we have the betas, and the betas are basically your coefficients. Your x values, these are all the values of your the x values are the values of your data. So this is how you can define a hyperplane. Pretty much in this gradient descent process, what you are trying to tune are the hyperparameters of this hyperplane. So to contrast linear regression, where we were trying to figure out the best parameters to create a line, in this case, we're finding out the best parameters to come up with that dividing plane for our feature space. So as a 2D example, we have all of these blue points, all of these purple points. X1 is a feature, X2 is also a feature. The class is determined by, let me zoom out so we can see this image. The class is determined by the color of the dots. So in this case, where our data is nicely separable, we can create this plane that divides our blue and purple nicely. In this case, we only have two features, so we can demonstrate it in 2D space, but if we have one more feature and it becomes 3D, very, very similar concept. We just need to take a plane, divide all of our data points. Any questions about this overall concept of dividing with the hyperplane? And hyperplane is just, that flat surface in feature space. All right. Okay, so the first classifier that we're going to talk about is a maximum margin classifier. So again, instead of using probabilities like some other models do, we're going to construct the hyperplane to directly separate the classes. As an example, if we have this data, purple class, blue class, these are all planes that successfully separate our data. Great. So in some cases, you can have many different planes that will separate your data. The idea here is to figure out what's the best plane to separate our data. Because if we had some test data points, and let's imagine our test data points belong here, whatever plane you choose will change the result of your classification on your unseen data. So it's important to choose the right separating plane. So how do we do that? And how do we know that this is the best plane? So problem with this approach, we can come up with an infinite number of hyperplanes so as we can tilt the line back and forth and it will still serve the same purpose. So we're going to use the hyperplane such that it would be the farthest from the training observations on either side. So the intuition here is if we chose a hyperplane that is far away from training observations, it will be far for the testing observations as well. So how do we compute distance? Let's just say that this is our data over here. The distance that is being reduced using gradient descent to decide on our best parameters is, let's just say with this line over here. With this line over here, we're going to take the 90-degree distance between every point and the line. So, all right, let's just add this distance plus this distance plus this on this side, and same for this side as well. We want to make a 90-degree angle between the points and the line. And that's going to be the distance for this particular plane. Now, what about some of these other planes? Let me change the color so it's a little clearer. So let's just say we have this plane over here, which based on this graphic is the better plane. So what we're going to add now is these distances. So you can see that the angle between the points and the line changes depending on the hyperplane that you're choosing as well. So here, basically, we're going to sum up all these distance, and the best plane that we want is the plane that gives us the largest sum distance between points and the line. Because if you think about it, if you're trying to separate something, you want a lot of leeway between your data points and that separating plane or line. So by that logic, that's how we decide on the best plane. And very similar gradient descent procedure as we did for linear regression, as I was mentioning. Instead, we're just adjusting this dividing plane. Any questions about this? All right, so this distance between the training observations and the hyperplane is called the margin. And specifically, the margin is the closest distance that you have to the plane. So if I quickly clear this and we zoom into this line over here, the margin for this classifier, and let's see, I think the closest data point would be this one over here, this data point over here. So the margin for this plane will be plus minus that distance. So in terms of terminology, that is the margin. So the classifier is basically aiming to find the maximal margin from the hyperplane that separates the training examples. Pretty much the same thing in different words. Questions about this concept idea? Okay, so if you want to get into some of the math of it, basically you're trying to optimize this equation. We're maximizing m, and m is basically this distance over here, subject to this constraint that all of your coefficients actually add up to 1. What that means is not important, but basically we're trying to figure out a classifier such that the maximum distance is, this is basically maximized. That's what that math equation is talking about. Details not very important for now. So yeah, questions about this before we talk about cases where you can't perfectly separate your data.
So is the purpose to have the data points far away as far as you can from the hyperplane? Is that the?
That's correct. That's correct. So in this 2D case, this middle black line is the hyperplane. And this is the hyperplane that has the smallest distance between the points and the line.
Okay. All right.
Sorry,
thank-
largest distance, sorry.
All right.
Yeah.
Thank you.
You're welcome. All right. Okay, so what if we cannot perfectly separate our data? So even though the maximal margin classifier looks like an intuitive idea and not too difficult to optimize for, might not be desirable under two circumstances. First, it will be very sensitive to individual training observations, because in this case, the maximal margin classifier does assume that you are unable to have anything on the wrong side of the plane. So let's just say you have this outlier over here. So the differences between this and this diagram is you have this additional point over here that doesn't exist here. With this additional point over here, you can see that the hyperplane makes a pretty big shift because you can't have points on the wrong side of the line. So it's very, very sensitive to individual training observations for that reason. Also, the algorithm will not converge. This specific algorithm will not converge or will not be able to solve anything if the training observations cannot be linearly separated. So let's just say instead of it being pretty clean like this, if we are in a situation where we have some purple points up here and some blue points over here, this specific maximal margin classifier will not be able to even solve itself. So therefore, what do? We move on to soft margin. So again, what happens if we can't come up with a hyperplane that perfectly separates training observations like the one above? First, we can use a soft margin classifier that we use to loosen up the definition of the margin. So this is an example of a data set where it's not perfectly linearly separable, right? There's no way to construct a line or a plane between these data points such that all the blues on one side and all the purples on the other side. All right, so rather than seeking the largest possible margin, so every observation is not only on the correct side of the hyperplane, but also on the correct side of the margin, we instead allow some observations to be on the incorrect side of the margin or even on the incorrect side of the hyperplane. So now when we construct our margin being, this minimum distance, we give it some leeway. We allow some data points to fall on the wrong side, but within this boundary. Things to point out. So in this example over here, you see that, okay, cool, everything's perfectly separable here. But on this, where it is not perfectly separable, we have a blue point over here. We have a purple point over here. And as you can see, they're technically supposed to be within this margin as much as possible. So adding this soft margin to it basically gives it some leeway. It is a lot less sensitive to outliers. You can think of it as a way to combat the overfitting problem of a maximal margin classifier too. So this is soft margins. To be honest, soft margin classifiers is one way to get over the issue of maximal margin classifier. But the next thing we're going to talk about with the kernel trick that I have been alluding to since the start, that's actually what's more commonly used. But anyways, here you can see that, well, it's not very straightforward, but basically these are the same equations as the one before. The only other thing we have here is we're including this leeway for the margin. The math to it, not important for now either. But yes, any questions about including the soft margin before we talk about some more details with regards to the soft margin? All right, sorry, I've been talking a lot all day, so I need to keep drinking this tea. Okay. All right, so if you're using a soft margin classifier, one of the hyperparameters that you can tune is how much leeway you want to give to your margin. So here, this hyperparameter E or epsilon is known as slack variables, which is how many training observations we allow to violate the rule of the margins or the hyperplane. So the amount of slack is bounded by C accordingly. So what does that mean? It's sort of like a regularization parameter. If epsilon is equal to 0, then we're saying that the ith training observation is on the right side of the margin. If it's less than 0, it's violated it, and if it's more than 1, it is on the wrong side of the hyperplane. So what we're optimizing for here is a combination of these three things, that something is classified correctly, something is classified incorrectly, and something is way past the margin. Right. So with cases like this, you can have different values of C. And with different values of C and how much slack you allow, your hyperplane will also change. So if we have, in this case, a very large value of C, you can see that we're allowing a lot of things to be on the wrong side of the margin. So you can see all these blue points over here that are being allowed on the other side of the margin. If we allow less slack and then less slack down here, you can see that the margin completely has rotated, just to allow for different levels of allowances. Cool. So it is like a regularization term. C, actually very similar to, I believe, in logistic regression, C is inverse regularization. So when you're working on the implementation of an SVM, higher value of C is less regularization. So it does say that on the documentation as well, but something to take note of. All right, so important to point out that in the support vector classifier SVM in general, only the vectors on the margins are used for classification. These are called the support vectors. So what that means is support vectors is because the way that we compute this distance is actually using vector math. There is one lab in this topic that has you do it from scratch. I don't recommend working through that lab just because it's very, very mathematically tedious, but just know that in order for it to efficiently compute the distances, it's actually creating vectors from the point to the line or from the point to the margin. That's how that's being done. Anything to clarify before we move on to the next part of SVMs? All right, so the next thing is really interesting. It's very mathematically complicated and can be quite abstract to think about, but this is what makes SVMs very, very powerful. And actually is what makes SVMs kind of perform almost like a neural network, which is really interesting. So an example to illustrate the power of this kernel trick is, and by the way, the kernel trick is what I was talking about enlarging the feature space. So sometimes we might have training data that's not able to be separated even with a softened margin, right? What if we had data that looked like this? If our algorithm was, something linear like an SVM, this is very, very difficult to separate. If we had a decision tree, this actually would be a lot easier, or any sort of tree-based model, which is why sometimes it's important to inspect your data for this reason. If we had a decision tree, we can actually, partition our data set to look something like this, and we'll be able to separate out our different classes. However, if we're just looking to construct a plane, this data is very, very hard for an SVM to separate without any additional enlarging of the feature space, which is what we're going to talk about. So even with a softened margin, as you can see here, there's a bit of a margin. This data set very, very difficult to separate. So the intuition to find optimal fit is called feature space expansion, or the kernel trick. It's called the kernel trick because it enlarges the feature space with a kernel. So the idea here is we're going to enlarge the feature space, and what enlarging means, I'll show some examples in a bit. And then what we're going to do is we're going to fit a support vector classifier in the enlarged space, and then we have a non-linear decision boundary in the original space. So this is a very common example used to illustrate how the kernel trick works. Here you can see that we pretty much have data that to us makes sense how we would separate it, right? Like just looking at this data, if we could draw our own decision boundary, we would draw it somewhere like this. We'll probably draw a nicer circle in real life, but we can say, all right, yeah, anything that is within these values of x2 and x1, that's blue. If it's outside of these values, it would be x1. For us, visualizing this from this perspective, very, very easy to see. For a support vector classifier that's trying to construct a hyperplane, not so much. So therefore, what the kernel trick does is it enlarges the feature space. Now that part can be a little bit abstract, but for this, we're like, okay, how can I represent this data slightly differently for a hyperplane to be constructed to separate this data. So what will happen is part of the gradient descent procedure as well is for this machine to look up different ways to enlarge in this feature space. For something like this, one possibility is like, all right, maybe I just add an additional dimension that keeps track of the values of X and Y to separate the red and the blue. So this idea of enlarging the feature space, maybe they're like, okay, let's say we have Z equal to 0, Z equal to 1, two possible values for Z. If my X1, X2 values are within this area, we'll do Z equal to 0. If my X1 values, X1 and X2 values are in this outside area, we'll have Z equal to 1. That's a very, very simplistic way of explaining the kernel trick, but we're enlarging this dimension such that now in this 3D space, you can see it's very, very obvious how we're going to separate this data, right? Because now we can pretty much cut our plane between these two circles of data points and separate our data. So what has happened here is we have been able to separate the data by enlarging the feature space. And this enlarging part is actually also done through gradient descent, so we don't have to worry about it at all. But that's being done automatically for you. There is a mathematical, oh yeah.
Vishwan, so every time the kernel trick happens, is there the possibility that the machine is going to add one more dimension?
Yeah, always. The machine is always adding dimensions. However, you don't see that new dimension. That dimension is never visible to us because after this is done, and let's say we have managed to separate our data, and if we plot our data, if we're not using the kernel trick, our decision boundary would be a straight line using an SVM or an SVC. If it is
on the visualization, we can always use 3D versions to it.
Yeah, but then I don't think you can actually extract the kernel itself from the model, unfortunately. So to us, if we were to plot the decision boundary, it'll still just look like a circle like that. We won't get to see what the exact equations are to separate the data into higher dimensions. Also, there are different kinds of kernels, and some of them are very, very intricate, and you might be adding like dozens and dozens of dimensions on top of this. So because of that, it's not something that we can visualize.
So when we are going to add kernels to it, what happens to the time taken for
The model to run?
Yeah, when you run with additional kernel, if we are going to run the program, it's going to take much more time than the normal, correct?
Definitely. SVMs, including basically non-linear kernels, and linear kernel is basically is no kernel basically. So non-linear kernels, SVMs take notoriously long to run because it's trying to figure out, all right, what are the best new dimensions to create such that I can linearly separate my data.
Okay.
Yeah. All right. Okay, so this is some more math on the kernel trick, which I don't think we're gonna skip through this. If you wanna see more specifically how this math comes into play with the kernel trick, it is actually part of the statistical learning book. So the statistical learning book, the one that I've linked on our homeroom page, they have the derivation of those kernel equations because I think it's not really worthwhile to go through during this time. But basically, there are a lot of different kinds of kernels. If we take a look at the SVM, if we take a look at, oh, that's a regression. It's scikit-learn SVC is what it's called. Okay, so support vector classification. So here we talked about the regularization, inverse regularization, which is what I talked about earlier. But in kernels, there are many different kinds of kernels that you can use. So this would be one of the hyperparameters that you actually tune. So there's linear, which is the regular straight line through it. But there's also RBF. RBF, I think, is a radial kernel. There's a polynomial kernel where it'll try to expand your feature space with polynomial combinations of your existing features. Sigmoid, pre-computed, these are all things that you can test to enlarge the feature space in different ways. Yeah, and in terms of the polynomial kernel, you can also include a degree. Any questions about this? Okay. Oh, and by default, it is L2 regularization here. Let me see this. I don't think there's anything else that's very important out of here. All right. Cool. All right, so there are different kinds of kernels. As I mentioned, the default for SVC on scikit-learn is actually the RBF radial kernel. There's a polynomial kernel, which is basically the way that they construct these additional dimensions. All right, so any questions before implementation? The implementation part, this will be very straightforward. So I'm happy to answer questions about the project after this. All right, so our usual libraries that we have here, the data set that we're going to use is the banknote authentication data set, the same one that you're using for the testing your functions. So this is our data. We have our shape over here, give it our column names, train test split. You can see I'm doing an RBF kernel and we'll look at the runtime. Cool, because this is a very, very small data set, it's much faster. And then pretty much we've seen this already. Your confusion matrix, which we can actually use plot confusion matrix here as well, and our classification report. And this is just on our test set, but I think all of you here have seen your functions, I think. Yeah, so I think you all are familiar with this. All right, so in conclusion, SVMs are very, very effective. However, it's not very highly interpretable. Now, because we are creating these brand new dimensions that don't really have any interpretable meaning in context, you lose that interpretation. Yes, you can actually get coefficients out of SVM, but sometimes the coefficients are not linear and therefore they don't really have much meaning. It's not as directly interpretable versus something like feature importances, where it literally tells you this is the important feature because it reduces this percentage of the entropy that we had in our data to begin with. The optimization is also hard to understand. The optimization in terms of creating the plane, that's easy, but the way that you have to use the kernel trick to increase your number of dimensions, that's very difficult to understand. It also performs very well on high dimensional data sets with a low amount of observations. The reason for that is because it's trying to look for a plane to divide your data. The more dimensions that you have, you can think of it as the more space your plane has to test itself and find good places to divide your data. So typically you have a lot more columns relative to rows, typically it works very, very well if you have more of like a wide data set, but we're not really dealing with wide data sets here. But if you have higher dimensional data sets, typically SVM performs better. However, typically takes a long time to run because of the kernel trick and all of that. Something that is used very commonly hand in hand with SVM is this other thing called PCA. And we're not going to talk about PCA for this phase, so you can pretend that I didn't even mention that, but that will be the first thing that we talk about in phase 4. So if you remember that there's something that makes SVM a little bit more efficient, it is the first thing that we're going to hit in the next phase. But yeah, that's our final model for phase 3. Pipelines I've spoken about a couple weeks ago, so that is all good. Any questions to wrap up all of our phase 3 study groups?
Quick question. Is this like SVMs more useful for like text processing? Or like what use cases would they be useful for? I would think that's probably.
I think for in terms of context, there isn't really like an industry that SVMs work well for. SVMs do have a good chance at performing very well for text data, because you're right, like text data has, if you think about our text data, if like every word is a column and you just have like word counts, yes, SVMs will perform very, very well because you have such high dimensionality. There's a lot of space for your SVM to look for a dividing plane.
I agree to that because the project which I did for the tweets, right? The SVM gave one of the best results. So, I mean, if you're going for any kind of text project, right? I think SVM should be the one which you should be actually looking for. Others are always there, but then SVM really works best.
Yeah, so SVM works well in dividing text data, as Kishore was mentioning, yes, because text data is of such high dimensionality. Some downsides though, for using SVM, you lose the interpretability. You also, it takes a very long time to figure out the dividing plane. If you were to use PCA with an SVM, it does speed that up by a good bit. So we'll come back to this at the start of the next phase. But yeah, thanks for sharing, Kishore. I forgot that that you use SVM for your last for your products. Yeah, anything else? All right, then let me stop the recording here.